good afternoon, everyone. Thank you for being here. So I'll make a brief introduction about myself. I am a physicist, and right now I am finishing my bachelor at Universidad de los Andes in Systems and Computing Engineering. Regarding my background, I have a very big passion for computational astrophysics, also computational infrastructure, and high-performance computing. And right now, I'm going to talk to you about AMUSE, especially because 3 years ago, I made an internship in the Netherlands working with this software, and I wanted to spread it, and especially because it's a Python software. So let's get more to it. My talk will be around 30 minutes long, so if you have any questions, I'll be happy to answer them at the end. So what is AMUSE? Why am I here today? AMUSE stands for Astrophysical Multipurpose Software Environment. What it is a framework, a software framework that allows you to make astrophysics simulations in a very straightforward and easy way. It contains a very wide library of community codes that go from different ranges of astrophysics. Some codes are written about stars, others about gravity. It involves different domains, and you can easily couple them together to make a simulation of a very complex systems. And when I say simulation, what I mean is you have a question to answer. You are thinking about a particular problem, and you want to see how, maybe with the right initial conditions, how it would evolve in time, which velocities can some particles have at the end, or where is our solar system going to end up in the long run. Things like that is what we want to answer with simulations. We want to have them as a tool to make science. And these codes that AMUSE has within it are trustworthy in the way that they're very tested. The people that publish them, they are experts in their fields, and you can trust to a certain level that what you're using is very high quality software. Apart from this, and especially because of PyCon, it is a Python interface, and AMUSE, its structure is Python built. So it's super friendly to the user, and it's very straightforward to learn. And finally, it's open source. So anyone can download it and can contribute to it, which I hope that by the end I encourage you to. And then, well, we'll keep talking about it. The 4 domains that I was talking about earlier are stellar evolution, hydrodynamics, gravitational dynamics, and radiative transport. And within those domains, there's a really big list of available codes for you to use. So I'm going to read this part. This is Simon, the person who said this, is one of the creators of AMUSE, if not the main contributor. So what is the objective of AMUSE? The objective is to do science, to explore scientific questions, to seek new boundaries and explore the new physics by means of simulation, to enjoy the joyous parts of computational astrophysics, and to worry about the nonlinear couplings between physical domains without having to worry too much about the details of the energy conservation in a closed three-body interaction. So in summary, what it says is we want to do science. We don't have to be worrying about writing a solver that a lot of people have written, that we know how to solve some special differential equation, and everyone has done it. We don't want to rewrite that again. We want to be able to use it in an easy way and implement it in a very complex project. Like to use your time as scientist as to obtain results and not to write code that has been done earlier. So the way people came to AMUSE, the reason why they built them, it's interesting. So it all started, like most of science does, with a beer. So two colleagues and other astrophysicists were talking in a little terrace in Italy, and they were discussing that they had this particular software called StarLab that was very good tested, that they made a lot of research out of it, but they wanted to expand it. They wanted to evolve more physical phenomena, and they did not see the way of doing so without having to completely rewrite their code. So they asked themselves, like, why? Why should we, if we already tested it, if we use it, if it works, why should we have to write everything all over again? There should be a way to like implement more science into it without having to do extra work. So, well, they took this idea back to the Netherlands, where Simon is from, and they created a workshop. They made a workshop in Amsterdam. They invited a lot of colleagues, a lot of astrophysics, people from the scientific community and the computation community, and they told them the idea. So one of the attendees was a Python fanatic, and he said that it was a very special language to like make people interact, and the thing that should glue together all of these different softwares should be Python. So they did, and they created a first version called MUSE, without the A. And when they saw it had potential, they created a whole team. They've hired software engineers, they hired scientific programmers, and to this day, it is a very well and composed team made of very smart people that I had the chance to meet, and they made what AMUSE is now. So let's get deep into what can you actually do. So as I told you, AMUSE has a lot of available codes that you could use. So I'm going to show you an example. Give me a second. Here. So what we see here is a three-body interaction. So let's imagine you have, for example, 3 stars, and you place them in a particular position in space with some masses, maybe some velocities. In here, they start in rest. And then you just want to see how they would evolve in time, like see how gravity would make them interact. So AMUSE lets you do that without having to write the problem that interacts gravitation, because that's known already. And you can see the evolution. Here there are 2 colors, red and black. Now we can see them, because sometimes, and maybe for people that have some relation to numerical solutions, you can solve a differential equation in very different ways with very different strategies, even if it's the same problem. And maybe some of them will diverge depending on the accuracy and precision that you want to reach in your problem. So sometimes maybe you make a delta t, the time smaller, or something like that. So you can not only choose like the problem of gravity, but you can also choose different solvers that solve the same problem. So here we see both. And that's something that, even though you could like estimate or predict, that's something that you actually want to see, because in astronomy we don't have the chance and the luck that other sciences have. We cannot experiment. We cannot like put 3 stars in a laboratory and see what happens. So we use computation as the greatest tool to like imagine why our universe is the way it is, and if our hypotheses are correct, if what we think form our solar system maybe, well, is the right reason. Okay, so this is the problem, and now the way to do it with AMUSE, I want to show you the snapshots of the code. Is super simple. So I just took one solver, the red one, and it's basically 3 parts. The first part is you import the libraries, you import the codes you want to use. You search, okay, I'm interested in this way of solving this equation and this 3-body problem, so let's import all of the libraries. You also import the auxiliary functions, something that handling units, because in basically all of science, units are very tricky to model when doing simulations. You get confused. It's not trivial to do them. So AMUSE also takes care of that. And then you initialize your system. You say, I'm going to put 3 particles of masses 3, 4, and 5, for example, and put them in this place. Later on, you create a function or several functions that tell the software how your system is going to evolve, for how much time, maybe how many snapshots do you want to take. And finally, you just have your main, and you run it. And maybe you plot some results, and then you analyze the data that comes out of it. And that simple script that, I don't know, maybe 40 lines of code, that created that whole simulation. And you can do science from that. But then this is a basic sample. This is only just one interaction. I'm not here coupling things. But let's see a more complex example. Let's say you have 3 stars, not a binary system, but 3 stars together, and you want to see how they share their masses, because the stars are burning material, but at the same time they're moving the way the 3 bodies moved. So let's model that same situation of the 3 body, but with some mass exchange between the stars. So you can see how 2 different phenomena, completely different phenomena, can be very easily coupled, and you did not have to write any of those codes. You just have to combine them in a straightforward way. And a particular thing about all of these codes that AMUSE use is that they can be written by anyone in any language. Well, it has a little bit of restriction, but they can be written in C, C++, in Fortran, in Python, in Java. It can be any language. The person who wrote it doesn't have to, they have to document it, but you don't have to understand their code. You're just calling it. And there's a whole interface that the AMUSE people created so that you can access them very easily and in a generic way. Okay, I'm going to stop it, but you get kind of the idea. So now let's get more into the structure of how they build this. All of this, except for the codes that are generic, all of this is written in Python, and the way you interact with the program, as you saw, is also in a Python script. So it has 2 top-level components that are the user script, that is what I showed you earlier, and the community model that has all of the structure of how you're going to communicate with the codes. So to begin, the user script is what I said earlier. You provide the initial conditions, you write the systems you want to couple, you say which codes, and then you communicate with the community ledger, the community component that I will tell you in the next slide. So it has 3 parts, as the previous diagram. The manager is which connects the Python model to the communication layer, the Python script, sorry. So it handles unit conversion. It handles unit conversion. So as all of the scripts are written in different things, they cannot accept all of the inputs of numbers you put them. So this takes any unit you put to a program and converts it to what each particular code needs. It also contains a state engine and a data repository that makes the data that you flow across models between them and with your user script consistent with each other. It also handles the exceptions. The manager itself is actually kind of, you can avoid it, but they don't recommend it because it does a lot of helpful actions that you can take advantage of. For example, exceptions. Each program handles exceptions and throws you exceptions in a different way. So you want to have a generic way to read them. Later on, you have the communication. So the people from AMUSE had the job to connect Python to any programming language available. And they chose a specific protocol to do so. So they chose MPI, the message passing interface. Maybe some of you that have worked with parallelization have heard of MPI. And what it does is that it has 2 parts, a proxy and a partner. So the proxy takes all the Python commands that you write and creates it and translates it into MPI messages. And then the partner takes those MPI messages that are decoded and turns them into any language that you need from the community codes you chose. And it's bidirectionally. They chose MPI because it's super widespread. A lot of people know that, and a lot of programming languages have bindings to MPI. And it is it runs well in a lot of platforms, like clusters or a simple computer in different things. And it has a bonus that when you want to parallelize or to run your code in a bigger infrastructure, more than a laptop, maybe you want a cluster, for example, it is naturally parallelized. So you don't have to worry about that distribution of load for the computer. And finally, we have the community code ledger. That is what has the code itself, all of the solvers that you want to use. And as I told you, it can be C, C++, Java, and a lot of languages as long as they have MPI bindings. That's the only requisite for the community codes. And they usually are, well, as I told you, well tested and also optimized. So the team tries to guarantee that they're going to take as little time as possible running. Okay, so why Python? Why did they choose this language? Well, not only because of the PhD student, but also because it's very broadly accepted. In the scientific community, there has been a constant and even accelerated increase in people to change their previous programming languages, maybe Fortran and others, even paid software, to Python. Right now, all the universities, well, not all, but most of the universities, they programming courses that have to do with astronomy are beginning to translate them to Python. And it's very friendly to use. I mean, you all know it. We all use it. Apart from this, it's object-oriented. It accepts object-oriented design, and that's the way all of the layers that I mentioned earlier are built. It also allows rapid prototyping. You want to take as little time as possible programming when you're doing astrophysics. You actually, what I feel and what most of my friends feel is just like an urge to have your code tell you, I'm ready, like check my results. Because even though the programming part is very amusing and that's something that I really love, you want to extract information that tool has helped you get. So it shortens the software development cycle. And finally, you get an easy access to the community code. As I said, you might not even a person that knows C might see a code written in C and they don't know what they're doing, even if it's documented. Like, it's hard to understand everyone's code. You understand your own, so you want to access to that without understanding it, just to interact with your user Python script. So to conclude my talk, I want to invite you. I know that you come from all different ranges in science, engineering, and other areas, but computation is a tool that lets us be the master of our own universe, even universes if you want to model. So if you're interested in these topics, astronomy, physics, science, or anything, Python is a great tool. And I hope that you get excited about AMUSE, that it's a very well-written software that, in my opinion, needs more spreading in the world. So yeah, thank you a lot, and if you have any questions, I'm available. Okay.
¿Y en español? Okay. ¿Español o inglés? Inglés.
Como quieras.
Well, that all was in English, so I will ask in English. Well, maybe it's not very relevant because, or maybe it's, I don't know. But I just read that you have 22 years old, right? And you had a major in physics, and, your major is in physics, and your second is in systems engineering. You're talking with such property of your development, and your English is fluent, and you don't seem like 22 years old girl. So what is the fault, or I don't know, the key that you have done? Because I teach programming here for other engineerings, and they don't have the passions or the skills to learn and apply what they are learning to their topics. How have you done it? What's the key for you?
So I don't know, I guess, something that driven me a lot towards programming, I actually ended up in programming by accident. I was very passionate about astronomy, and in a very fanatic way, I did not know anything about it when I was in school, but I really liked the idea of considering just our universe and the place where we're standing. And when I started physics, I started in that major, not in systems and engineering. I, well, they gave us this tool to like make experiments. And then I figured out there was actually the way to, I could create anything that I wanted. As I told you, I could create my own universe. I have modeled galaxies, and it's so nice to like be able to reproduce something that takes like billions of years into making in, I don't know, maybe a code that takes weeks or maybe days to run. So I guess I started in computation by my love for astrophysics, but right now I also ended up very interested in, like I said, security subjects or other engineering areas. But I don't know, I guess the key is, well, this sounds cheesy, but it's like passion, like just enjoy what you're doing. I imagine if anyone in this room does what they want to truly do, everyone would be excellent at it.